Welcome again, this is Dr. Ali Mugable and we are doing graphical convolution. Some are finding it difficult, so we'll start with the basic meaning of convolution and then we'll go right away into graphical examples. We'll do one example in details and two more examples with less details. So let's start. Graphical convolution is the implication or the implementation of the convolution integral. So we need to focus on this integral. In other videos we might discuss why we get to convolution, but now what you see in front of you is the convolution operation, and on the right hand we have a couple of operations to be done. To start with, convolution is done between two signals or two functions. The first thing you need to do is to replace the time variable with a dummy variable, let's say tau or lambda. Then we need to flip one of the signal around the y-axis. Convolution is can be done f1 convolved with f2 equal to f2 convolved with f1. So it's commutative operations. You can flip the order. Second, after we flip the signal, we can shift the signal that we have flipped by a factor by a time variable t. Then after we flip and shift, we multiply the two signals as in the integral. And finally, we find the area under these two products. We find the integration of these two products. So in principle, there are four operations: shift, flip, shift, multiply, and integrate. Now the result that we get is only at that specific shift, t. Then what we need to do is to change the shift, repeat the operation, and the answer will represent the convolution at the new shift. Okay, we are now seeing the integration expression, but we'll do all these operations graphically. Let's start with this example. It says convolve the following two signals, two functions. And I picked some moderate functions, not too easy, not very difficult. So we have f of t and g of t. Now, if you want to find the convolution, the first step we do is to change the time variable into tau. As you can see the diagram, I have changed from t to tau. Then we need to flip the signal. Our choice was to flip g of t, so you cannot see the effect because we are mirroring the signal around the y-axis. And the signal is symmetric around the y-axis, so this is not going to show. If you have flipped the other signal, it should look like this. So we have line here, this is going to be -2, and so on. But we are choosing one of them, so we picked g of t because it's simpler and symmetric. So the third operation is to perform the shift. So once we shift, you can see here that I have changed the time index. This was 0, this was 2, and this was -2. Now everything is shifted by amount t. Our reference 0 is shifted, is now becoming t. Everything is shifted accordingly. Now if we want to multiply them, we'll observe that they're going to overlap in general. So they look like something like this. And we have different possibilities for the overlap. The signal could have started here or there. So we'll examine what are the possibilities of this shift before overlapping, before multiplying. So we have done changing the variable, we're done with the flipping and shifting, but before we multiply, we observe that the two functions could overlap fully or partially, or they may not overlap. So let's consider all possibilities. Now we continue with the graphical convolution example. We can divide the convolution into different parts. We'll see why we have 5 parts. To start with, if you look at this figure here, we're taking the purple signal and we are shifting it from left to right. Okay, so we're starting from -infinity and then we are moving this signal in this direction. So if you notice here, the red signal starts at this point, which is t equal to 0, while this index here is 2 plus t. So as long as 2 plus t, as long as 2 plus t is less than 0, as long as this point is less than this point is less than this point, then we can say that there is no overlap. We can solve this inequality, which says that t should be less than minus 2. So the first observation is, as long as t, the first part, as long as t is less than minus 2, what you get, the two functions do not overlap, and the result of the convolution is going to be 0. So we have solved a big part of the problem. For t equal to minus 3, minus 4, minus 5, minus 6, whatever, you're going to get 0. Now, in the second case, the second part, we have partial overlap. So in this partial overlap, okay, it will start as the next when t is greater than minus 2, but up to what? Up to 1. You can see here, so the width of this purple signal is 4. We have 4 here, units. And this one is just 2. So we are focusing here, as long as this point is less than this point, we have this partial overlap. So as long as 2 plus t is less than 2, which means t less than 0. So this will continue from the previous limit up to t equal to 0. So we are taking the limit from minus 2 up to 0. In that case, multiplying the two signals, performing convolution means multiplying the two signals. The purple signal is constant 3. We are talking about this overlap region. Okay, this is the region of the overlap. So if you want to perform the integration, okay, we are going to get the following limits. The integration is from 0 to 2 plus t. Okay, this 2 plus t changes, and this is how I got the integration limits. Many students find it difficult to find the integration limit, but this with the diagram should help you out. Now, also the colors here matches. I'm multiplying the two signals. This is 3 constant signal, and the other one is a straight line equation. You should be able to draw or express this line in terms of mathematical expression. It's a line with a slope of minus 1 and y-intercept at 2. This is why we're saying it's minus tau plus 2. This is the slope and this is the y-intercept. So if you multiply the two signals, now the integration becomes relatively easy. You get minus 3 tau. You integrate, you add 1 to the exponent, and you divide. Okay, plus 2, it becomes 2 tau. 3 is still outside. You substitute the integration limits. It might take a little bit of time, but it's straightforward. We are substituting the integration limit. Instead of tau, we have 2 plus t. The other limits will give you 0. So opening the bracket, simplifying things, we got the following expression. So this will give you the convolution for any value of 2 between 0, minus 2, and 0. In the next slide, we'll continue part 3. In part 3, you can see here that we have full overlap. Remember that the purple signal is wider. It has a width of 4. The other one is just 2. Remember our last limit was 0. So this will continue to be true as long as we don't get outside. So this is 0 and this is our edge. So we'll have full overlap as long as minus 2, we're moving in this direction, plus t is less than 0, or t is less than 2. So the limits here are going to be from 0 to 2 as we have just found. Now if you multiply the two signals, we'll perform the convolution. We can see that we have complete overlap and the area under the product. Okay, the integration limits now, the region that's shared between the two is this region, right? Because everything is outside 0. So from here to here, everything outside when multiplied will get you 0 because this signal will be like this. So no wonder the integration limit is from 0 to 2. And then this function is the one is 3, purple, and the other one is minus tau plus 2. So if you multiply them and integrate, you get a constant. Okay, the limits finally will give you 6. The convolution is going to be 6 for any value of t between 0 and 2. We'll continue in the same way. You might start now guessing that the squares now start to leave. Now the shared region is from here to here. Okay, so, and this will continue until this gets outside. So until minus 2 plus t become, it will be true for minus 2 plus t less than 2, and that's up to t less than 4. Okay, we are having steps of 2 all the time because of the width of the triangle, the smaller one. So from 2 to 4, we get partial overlap. You can set up the integral. This is again partial overlap, and the integration limit will be done similar to what we have done before. Just to give you a hint, the integration limit now become from minus 2 plus t up to 2, because this is the overlapping region. And then you write the equation for the same expressions 3 and the same line minus tau plus 2. We're not showing the expression here. You can pause the video and try to find the expression. It's going to be shown in the next page, in the next slide. It's a good exercise, so if you want to test yourself, execute the integration and make sure that you get the same answer that we'll show in the next slide, because sometimes our problems is not in the concept but rather in executing the math. And then now finally we'll have the case when this triangle gets outside, and this is the last limit, the fifth partition, and of course at that case we'll have no overlap, so the convolution is always going to be 0. The two functions do not overlap, and we get the answer equal to 0. So let's organize the answer in the next page. So now if we put everything together, and I'm using colors to show you that we found there is no overlap region, it corresponds to this red part, and then we have the function that you have calculated. It becomes a second order because we multiplied the two signals. One was linear, one was, so we got the first order. When we integrate, it becomes the green part here shown, and then we had a constant. Make sure you get the right limits. And then this is the one that we did not show the expression in the previous slide. It's shown with yellow, and finally we have 0. What you see here is the result of the convolution. And so we have done the different parts. In the next slide we'll show some maybe simpler examples just to again emphasize the concept. But let's now try to check whether our answer is correct or wrong. Now, how to check whether the answer is correct or wrong? I'll just give you a few hints here. The first way to check the starting and ending points. I'm coloring them here now. You can see here that the starting point is here 0, and here is minus 2. Always I mean by the starting point where the signal becomes non-zero. You can see that the result of the convolution always start at the sum of the 2 points. So the first signal start at 0, the second signal start at 2, then the convolution must start as the sum 0 plus 2, which is 2. 0 and minus 2, and it becomes minus 2. Now, similarly for the ending point, again the end point where the signal now again gets back to 0. So this ends at 2, this one ends at 2. So this signal must end at 4 as a sum of the 2, which is, this is going back to 0 at 4. So fantastic. The first check applies. We can check the second thing. It says that the area of the convolution should equal to the product of the two individual areas. So what's the area here? What's the area of this triangle? Half the base times the height. So this is 2, this is 2, so it becomes 1 times 2, which is 2. The area equals to 2. Similarly for the second figure, the area here, height times width, so it's 4 times 3. Okay, so we have 4 times 3, which is 12. So I expect the area here to be 24. Let's double check. Is it really difficult to find the area? much, we can guess that if you take this piece here and slice it here, okay, so approximately, so we get a rectangle. How much is the area now? We have 4, that's the width, times 6, that's the height. This is not drawn to scale, of course. So you get 24. And that's another check, that the area of the convolution equals to the product of the individual areas of the signal that we have convolved. Next, we're going to move into some other examples just to verify the concept. Graphical convolution example number 2. Find the convolution between the following two signals. I'm sure you know how to sketch these signals. Okay, it's a rect. Okay, this is the width of the rect, and that's the shifting point. So basically, this is of course the scaling amplitude. So the first signal is shown here. This is the amplitude of 2. This is the width. Okay, and that's the shifting point. So I'm sure you can sketch the other one. The other one will be a unit of amplitude 1, and the width is 4, and the center is at 2. So if somebody says convolve these two signals, this is a much easier example compared to what we have. So the first step we do, you need to change the variable into tau or lambda. Then you pick one of the signals and flip. Then you start the shifting, multiply, and integrate. So the first thing you do, like for this example, I picked this signal as is. I flipped it and I changed the variable into tau. So now this is x of minus t. We have x and h. So now, in general, if you want to apply the shifted version, then all these times has to be shifted. So t0 becomes your reference t, and everything will be shifted by a factor of t. Now you keep changing t, and you multiply the two signals. Every time you multiply, you get the area and you get the convolution. For example, if you want to find the convolution at t equal to 2, you don't need to use the variables. You just, if somebody is interested only at one output of the convolution, like at t equal to 2, you can just substitute here. So this becomes 2 minus 4, this becomes minus 2. This becomes 2 minus 6, which is minus 4. So if you multiply these two signals, of course, in this case now you get 0. That will give you the convolution at one specific point. If you want to make it general, then you keep using the variable t, and we perform different operations. So how many cases are we going to get here? Okay, so remember that the width here is 4, and the width here is 2. So we get no overlap, then partial overlap, and then we have partial overlap, and then no overlap. If they had the same width, then we'll get just no overlap, overlap, or partial overlap, then partial overlap. They will not be full overlap because they have the same width. So let me explain what I said in more details. Now let's do the example in more details. Recall the function. How does it look? This is the h, and this is x after flipping. Now after flipping, we need also to apply the shifting. So for this shifting, we'll take the second signal and start shifting it in h. We start from the left and then move all the way. So as long as these 2 points does not intersect, which means t minus 4 is less than 2, or t is less than 4, always the answer will be no overlap, and we get an outcome of 0. And then now, after that, for t greater than 0, we'll start having some partial overlap. Remember now the width of this upper triangle is 4, and the width here is 2. So we expect a partial overlap will continue for 2 units, and that's true from 4 to 6. Now we can perform the integration. The integration limit will be from 0 to 4 minus 6. The function that you need to multiply is just basically constant, 2, and 1. So things here are relatively simple. We're not going to show all the details. And then you keep moving for 2 more additional units. You get full overlap, and then the integration limits are from here to here. And the reason this is going to end, this is going to be from 6 up to where this point reach here, or t minus 4 becomes, it will be true up to t minus 4 less than 4. So t less than 8. Of course, then now we get the same convolution when we have partial or full overlap. And then finally we have partial overlap from 8 to 10. And then we can summarize all the cases in the following results. Okay. You see here now that we have started the convolution at 4. We ended also at 10. If you compare the two original signals, they start at 0 and 4. The other one was look like this, 4 to 6. So you can see here that and amplitude was 2. So basically the starting point, which is 4 here, equal to 4 plus 0. And the ending point equal to 6 plus 10, plus 4, which is give you 10. So this satisfies the two starting and ending conditions. If you look at the area here is equal to 4 times 1, which is 4. The area here is 2 times 2, which is 4. So we expect the total area to be 16. Now if you look at this one, if you take this part of the triangle and slice it here, so you get the following triangle. How much is the area now? This is 4. This is 4. Of course, it's not drawn to the same scale. You get 16. So we have shown that this is the result of the convolution. You can do it in smaller steps, but some parts are relatively easy, which finding where we have no overlap. Sorry, and sometimes some, of course, areas are a bit more difficult. You can, as you get used to the graphical convolution, things become simpler. Now we'll look at one final difficult example, but we'll look at just the scenarios. We'll not execute the math. So it says now convolve the following two signals. You can see that we have more than one case, overlap, partial overlap, and what have you. So if you do the cases, you have, at least it's easy to find where we have no overlap. So then we have some partial overlap with the first, second, and then it keep going on. We'll consider all possible scenarios until we get out. So, and this is the exact solution. How does it look? Our objective is not to do things usually graphically by our eyes and holding the pen. But the idea is that this is the way to understand the concept. Those complicated ones can be executed with using MATLAB or any computer program. But we have the ability to verify and check whether the answer makes sense or it does not make sense. So the reason we are doing it graphically is not that we want you to do it graphically in real life, but rather to understand how things work. Now, okay, so we mentioned this point before. If you are interested in only one output of convolution at a given time, you don't need to do the full convolution. You can just make the shift to that point and do the multiplication. And also it's true that the only way to learn graphical convolution is to hold the pen and try to draw yourself. Otherwise, it is not going to be easy. Start with simple examples and then make them a bit more complicated as you go on. Thank you for watching, and we'll see you in coming videos. There will be another video, hopefully, about the meaning of convolution. What does it mean? Thanks again.